This conference will now be recorded.
Very good morning, students. We are back with the revision section of this current and electricity chapter. So we have picked up some good problems, numerical problems from previous year's IIT JEE paper, mainly 2019 we are doing now. So we have got this first problem here related to meter bridge. So let us see what this problem is saying. See, you can see this is a schematic diagram of a meter bridge circuit. Okay, meter bridge, which acts on the principle of Wheatstone bridge. Okay, we have discussed in the previous class Wheatstone bridge. Like we have solved few problems on that. So application, one of the application of Wheatstone bridge is meter bridge. And what we do, we actually use the principle of Wheatstone bridge and meter bridge to calculate unknown resistance. So here you can see there is a resistance box over here. This is the unknown resistance which we need to determine, and this is a conducting wire. Generally it can be a copper wire, so it has certain resistance, you know that. And see, the length of the this length of the wire is actually measured from this side. Suppose A to B, this is B, so length is measured A to B. So what we do generally, we connect the circuit, and this is a galvanometer, you know that. So galvanometer is connected, like one end of the galvanometer is connected to the jockey, and jockey can slide over this wire. This wire is of 1 meter or 100 centimeter length, so that's why this device is called, or this experimental setup is called meter bridge experiment. And here we will start sliding the jockey from A and go over it, and what we'll try to do is we'll try to get no deflection condition, no deflection in the galvanometer. That is called null condition, as you might know. So no deflection we have to see in the galvanometer, that is called null condition, or null condition also. So we have to find out at which length we are getting null condition. So while doing the experiment, we generally repeat the experiment to get more accurate result by averaging that out. First of all, let me write, say meter bridge, if you have the image of Wheatstone bridge in your mind, that would help you. I'll just draw that, and we'll compare with that actually. Okay, let us say this. Actually there will be resistance here. This is generally named as P, this is actually Q, and here this arm we have R, and this arm we have S. Okay, generally here there will be power supply. Okay, and between this end, so it is actually given A, B, C, D. So B, D, there will be galvanometer connected. Okay, and you can see that if I just, okay, let me tell you here. So at the null condition for this particular Wheatstone bridge, we write P by Q is equal to R by S. R by S, right? So in this case, we have to see which one is what. Here, this resistance box is actually acting as P. This X is actually acting as Q. This is this length L is acting as R, and the rest of the length, that was 100 minus L, that is acting as S. Okay, so comparing that we can get it. Now let me tell you about this table. This table gives some readings of the experiment. So 4 readings of the experiment, and here you are asked to find out which of the readings is inconsistent. Which of the reading is inconsistent? Okay, so look here, as the student slide the jockey, and at the same time this is actually the standard resistance box. So from where you can just uh, apply certain resistance. So when here 1000 is applied, the null condition is found to be 60. That means this length is 60 and rest is 40 centimeter. Okay, second case, the resistance box, when it is adjusted with resistance 100 ohm, then the null condition is found, a null position is found at 13 centimeter from this particular position. Okay, all right. So this is, say, A and C. This is A and C. This is B. Sorry, this is B, and this is D actually here. Okay. All right. So look, if we write down the condition for null position over here, so we get here actually R by X is equal to R by X is equal to L by 100 minus L. Okay, L by 100 minus L. Here it is L, so L by 100 minus L. This is what will get the condition for null position here with the given meter bridge. So I'll just erase this out so that I can use this space, and look here, inconsistent reading we have to find out. That means every time we'll do, we'll use this, and let me write what is X. X is actually 100 minus L divided by L into R. Okay, all right. So let us use these readings and find out the unknown resistance and which of the reading is giving what value of the unknown resistance. Okay, so I'll take first reading. Let us say this is case 1. Okay, case 1. So here L is how much? L is 60 centimeter, and this R is in ohm, that is 1000. So let us find out unknown resistance for this particular reading, first reading. So it is actually 100 minus 60 divided by 60 into 1000. Okay, so this is further, this will be in ohm anyway. 60,000, sorry, 40 into 1000 divided by 60. So it will be like this. 2, this is 3. Okay, so if we divide this 2, suppose I take 20, so this is, so it will be like this. Again 6 will come. Okay, so 6, 6, let us say 667. Okay, nearly. All right, so nearly 667. We take this as 667 nearly, and this is an ohm. Okay, so first reading gives 667 ohm unknown resistance. I'll just erase this portion. I'll just use these values. Okay, so here see, second case, this R is 100 ohm and this length has become 13 now, 13 centimeter. Okay, so this is reading 2, this is 13 centimeter. So let us 13 centimeter again here. This is 100, so this will be 87 by 13 into 100. Okay, so this, how much this gives? Okay, let us divide this. This will give you 78, then it is 9. Further it will give this, again it will come like this. Then it will come like this. No, this I can go up to here 9, so 117. Here it will come 3, so it will come 2, like that. Okay, so it is actually nearly, and 100 multiplied, so it will be nearly 669 ohm. Okay, so the second gives 669 ohm. Now we'll see the third reading. Third reading says this is a 1.5 when the resistance is 10, adjusted resistance is 10, 1.5, 1.5, and here resistance is 10. Let us erase everything here. Okay, so if we just calculate this similarly, what we would get here? We'll get, so this is, so let us say 298, 97 point this. Okay, 97 point, sorry, 98.5, 98.5 divided by 1.5 into 10. What we can do is we can actually into 100 divided by 15. So this also, if you just divide with 15, so 6 goes 90, then it is, oh sorry, this point shouldn't be there. 5, 10, now this will come here. Okay, so it is again 6. So it is actually, if you look, this will come again around, this is actually 98.5. okay, 98.5. So if I multiply that 10, it will be like this, and here it will be 10, not 100. Okay, that's how you will get nearly 656 ohm. Okay, this is the third reading. So all three are actually coming nearby. Now look this. So case 4, x will be 100 minus 1 divided by 1 into 1. How much it is? It is 99 ohm. Is it coming nearly these values? No. So that's why the fourth option, fourth data is actually inconsistent data. So this is how we have to solve this problem. So the fourth one is inconsistent. Okay, we'll move on to the next problem. So this problem says a galvanometer whose resistance is 50 ohm. It has 25 divisions in it. When a current of 4 into 10 to the power minus 4 ampere passes through it, its needle pointer deflects by 1 division. To use this galvanometer as a voltmeter of range 2.5 volt, it should be connected to a resistance of what? Among these 4. See, I'll just draw a schematic of galvanometer. So galvanometer, it has some inbuilt resistance in it, and let me denote that with Rg. Okay, now look, this galvanometer has, see, the galvanometer pointer deflects 1 when this much current passes through galvanometer, then its needle deflects by 1 division. That means, see, if it has actually 25 divisions total, right? Total 25 divisions it has. So you know, for full scale deflection, what is the total current through it? For one division equivalent current is given here as 4 into 10 to the power 4 into 10 to the power minus 4 ampere, corresponds to 1 division. Then what is the allowed current? What is the current, maximum current allowed through the galvanometer can be found out. See, maximum allowed current, maximum allowed galvanometer current, allowed current through galvanometer is through galvanometer, which can pass through this, let us say that is IG galvanometer, is determined from full scale deflection. Okay, from full scale deflection. So how much division it has? 25 division. And how much like the current, like each division corresponds to how much current? This much current. Then what is IG? What is the current allowed through the galvanometer? That is the number of divisions, total number of division total number of division into this much current, because per division current is this much. Okay, all right, so this total division is 25. So what is the allowed current? Ampere. This is 10 to the power minus 2 ampere. Okay, 10 to the power minus 2 ampere. So I'll just erase this part, or let me go to the next page and write down. Okay, I think I don't have page in the next page, so I'll just erase this part. I hope you have understood this. I'll just repeat it and then erase. So I just need to find out what is the total allowed current or maximum allowed current through the galvanometer. So here in this problem it is given that the current 4 into 10 to the power minus 4 ampere can actually make a deflection of 1 division, and it has 25 divisions. So from here we can find out what is the total current which is allowed through this galvanometer, that is actually 10 to the power minus 2 ampere. So that we have obtained, and we don't know what is the Rg, resistance of the galvanometer, first of all. Okay, no, we know this galvanometer resistance is given. I'm sorry, it is given in the first line itself, a galvanometer whose resistance is 50 ohm. So Rg is also known. You can see Rg is also known. Rg means the inbuilt galvanometer resistance. It is not from outside source. Okay, it will be some resistance will be there, some internal resistance of the galvanometer, that is given as 50 ohm. Now when we have to use this galvanometer as a voltmeter, we know that we have to actually connect this galvanometer with a very high resistance in series, and that resistance, say Rs, this is G galvanometer, this is Rg, and what is the current flowing through this is Ig. See, when we have to find out the, like, if suppose here in this problem to use the galvanometer as a voltmeter of range 2.5 volt, it should be connected to a resistance. So look, the drop across this whole setup, the voltage drop across this whole setup will be that this should be 2.5 volt given. Okay, so I want to have this much voltage, range will be 0 to 2.5 range. Okay, so to use a galvanometer as a voltmeter, we have to first of all connect a high resistance with the galvanometer in series, and the total voltage drop across the galvanometer and across the series resistor will give you the range. That means, you know, Ig, which is passing through the galvanometer and the resistor both, Ig whole into Rs plus Rg, this will be actually 2.5 volt. Okay, now look, we know Ig what it is. We have to find out actually Rs. Rs is equal to 2.5 by Ig, okay, minus Rg here. Okay, look, then Rg known, Ig is known, so this is 10 to the power minus 2. Ig is 10 to the power minus 2, and this is 50. Look, then it will be actually Okay, this is in ohm. Two 50 minus 50 ohm. So which will give you 200 ohm. 200 ohm. Okay, so this has to be 200 ohm, and option C will be the correct answer for this question. We'll move on to the next problem. This is again a very nice problem. Okay, so an ideal battery of 4 volt and a resistance 4 like resistance R, capital R, are connected in series in the primary circuit of a potentiometer of length 1 meter and resistance resistance 5 ohm. So let me just tell you. So suppose there is a 1 meter length potentiometer wire. This is suppose 1 meter, and it has resistance 5 ohm. Okay, now this is connected in series with resistance R and battery, and that battery is actually an ideal battery. Okay, it has 4 volt voltage. The value of capital R of a potential difference. The value of R, sorry, the value of capital R to give a potential difference of 5 millivolt across 10 centimeter potentiometer wire. See, I have to use the same this resistor. Okay, to give the value of capital R to give a potential difference of across 10 meter potentiometer wire. That means, here it is given that the potential difference 5 millivolt is across 10 centimeter length of a potentiometer. Okay, potentiometer wire, right? Then what is the voltage drop across that particular wire? Voltage drop or potential drop, I should write potential drop per unit length of that wire. Let me just write a single line over here. Given potential difference of 5 millivolt. 5 millivolt is across 10 centimeter wire. Okay, 10 centimeter wire. Then potential drop per unit length. Potential drop per unit length, excuse me, per unit length will be 5 millivolt. That 5 millivolt divided by 5 millivolt by 10 centimeter. So potential drop per like this is 10 to the power minus 30, and this is 10 into 10 to the power minus 20, then it is actually volt per meter. Potential volt per potential drop per unit length. So that is what I should not write any unit over here, but anyway you can understand that this will be so 0.5 into 10 to the power minus 1, that means 5 into 10 to the power minus 2. This is the this is now volt per meter. Okay, this much volt per meter you have to actually the wire of 1 meter length would drop this much potential. So what I say is that 1 meter length of the potentiometer wire potentiometer drop will be how much then? 5 into 10 to the power minus 2 5 into 10 to the minus 2 volt per meter is the potential drop across each meter. Now the question is I have to use this to, okay, so this is fine. Now let us say potential drop. So look what was there. This is the capital R. It is connected with the ideal battery along with this 1 meter wire in series. Okay. Now look, if I know the potential drop is 10 minus 10 to the power 5 into 10 to the power minus 2 volt per meter for this wire. Okay, for this wire which is connected with in series with this. So then you know the potential drop across R will be potential drop across R. Across R is VR is equal to see 4 volt 4 volt 4 volt minus this much volt. So this much will be the potential drop for this across this capital R. Okay, this would give you actually. So if I bring it like this, so 395 divided by 100. Sorry, 100. So this is the voltage drop across the capital R. Now you have to find out what is the value of R. So we know we can now write VB is equal to IR. Not VB, VR is equal to I R if the current through the circuit is I. Okay. Now then we can actually find out what is I. I total R, so V by R. Here actually there are two things. Here total R is actually 5 ohm is the resistance of the wire. So that also we have to take care of here in series. Now we know this is actually R plus 5 R plus 5 into this is the current. Okay, this is the current. So I have to find out the resistance. So voltage drop. So voltage drop will be actually okay. Just a minute. I'll rewrite this part. So VR is equal to I into R total. Here you know this is 1R, this is having 5 ohm resistance. Okay, I total R. So here I we have to find out I VR by R total. And what is this R total? Actually, we know from here V of R. What is V of R? This we know already. And this then we can find out this is 395 by 100, and in the denominator you have R plus 5. This is what is the total current, right? So now what is VR is equal to? VR is equal to, then I'll just drop this figure. So 395 by into R, this is equal to 300. No, not this one. Anyway, this is actually okay. I'll just pick up from here. Let me just tell you, V of R is equal to this much is fine. This is voltage. Now I into R total, the circuit I drew there, because you know this is capital R, this is the wire, and this is connected with this. So wire has some 5 ohm resistance, and this is 4 volt. So what is the current then? Current will be actually V by V means here 4 by R plus 5 ohm. This is the current, and if we multiply capital R here and here R, so this will give you VR. This I into R is VR. So this is equal to 4. We have to find out what is the value of R. This is R plus 5. Okay. Now, if we try to calculate it from here, okay, let us go with that. So 495 R plus, sorry, 395 into 5. Okay, this is again 400 R. Okay, if you solve this, we will get actually this 395. This is the capital R, value of capital R. Okay, we'll go to the next problem. This is further an interesting problem, and it will be little lengthy also. We'll just continue this. See, let us first understand the question itself. The question says the galvanometer deflection when K1 is closed but K2 is open. Look, K1 is closed, this one is closed. Okay, this one is closed and this one is open. That means the circuit is now along this way. Okay, that means it goes, the current will flow, current will flow from the battery like this. Current will flow from the battery to this resistance, then it will pass through the galvanometer and it will come through this way like that. Okay, this will pass through like that when the K1 alone is closed, and that time the deflection is seen to be theta 0. This is the deflection, and generally we write phi as theta 0 anyway. On closing K2 also, on closing K2 also, this also will be here, and also, and on closing K2 and also adjusting R2, this R2 is adjusted to 5. Okay, now see, now I have both this K2, this is variable resistor R2, this is R1 say, and this is galvanometer over here. Okay, this thing is actually now connected to battery. So this is now connected to battery both. So this is R2 and RG. If I say this galvanometer has resistance RG, so R2 RG they will be in parallel. That the whole thing will be uh, parallel series in series with R1. So this thing is there. So if this is the case, see, along with that R2 there will be some resistance 5 ohm. The deflection of the galvanometer becomes 5 theta 0. Okay, 5 theta 0. Okay, so here K1 is here, K1. All right, so this is the question. Now you have to find out what is the resistance of the galvanometer. Given that, neglect the internal resistance of the battery. I hope you have understood the problem. So I have two deflections and two situations. I have to write down two equations and to find out two unknown things. Okay, here you have to find out RG. Anyway, let me clean everything and write down. See, let us say the current flowing is Ig. In the beginning, see, in the first case the current is actually Ig flowing through this resistor. Okay, and say, so this Ig is directly proportional to the deflection theta 0 in the first case. Okay, in the first case, direct proportional to theta 0, so I can write this Ig is equal to C theta 0 in the beginning when K1 is closed, that time. Okay, Now theta is the deflection of current, as you know. C is the constant of proportionality over here, and K1 is closed and K2 is open. So at this situation, what we have Rg plus R1. Okay, this is the total resistance. Okay, this is the total resistance. Okay, or equivalent resistance. So Ig can be written as the battery voltage of the battery divided by R1 plus Rg. Okay, this is equal to C theta 0. This, let us say, equation number 1. Now go to the second situation. In the second situation, let us say the galvanometer current is directly proportional to, again, deflection. So here deflection is 5 theta 0. Here also, let us say it is I is equal to C5 C theta 0. Okay, this is the current now through the okay. Now question is, on both K1 and K2 they are actually connected, then equivalent resistance will be R1, this is in series, plus R2 parallel Rg. This will be parallel resistance. Okay, Rg and R2 will be parallel to each other, which is in series with this R1. Let us write that R equivalent here as R equivalent is R1 plus R1 plus R2 Rg divided by R2 plus Rg. Okay, this is what we have got as equivalent resistance. Okay, now we have to find out what is the current through the galvanometer. Now current through the galvanometer in the second case will be, see, I know this is the equivalent resistance, so this is this. So this is the V by R into, here it will be R2 by, because you know this is the parallel circuit combination, this is in series with that. Okay, R2 by R2 plus Rg. Okay, so this is the galvanometer current, which I can directly write is equal to C 5C theta 0. Okay, 5C theta 0. So 5C theta 0. Now V into R2. So V by R2 plus Rg, V by R2 plus Rg. So look this part, we have already got something here. V by R1 plus Rg. Okay, V by R1 plus Rg is equal to C theta 0. So maybe we can make use of that also. Here, okay, this is not 5 theta 0, theta 0 by 5. Okay, so here it is 5 will be down. Okay, so this is the value here. I have got two equations. You can see that this is equation number 2, and here I have got equation number 1. Now these are actually both galvanic current. I can just equate them to get some relationship with R1, R2, etc. So if I just equate them, okay, equate them or divide them, we can just divide them also, no, doesn't matter. So let me just do one thing. I'll write the equation number 1 here itself. So V by R1 plus Rg is equal to C theta 0. Now from here, if we just use the theta 0 value, that also will help us to get the thing. So let me just find out theta 0 from here and put it here. Okay, if we put there, look what we get. Theta 0 value we put here. Theta 0, that means it is actually V divided by R1 plus Rg. Okay, and there will be C multiplied here. This C, this is same. They will cancel each other. This V will cancel each other. Okay, so finally we'll get an equation after solving this equations. Look what we get is R1 R2. If you just solve it, R1 R2 plus R1 Rg plus 5 Rg divided by R2 into R1 plus Rg is equal to 5, you will get. Okay, see, we can just do from here. See, this R2G will cancel each other. Multiply here R1 R2, this is R1 Rg, so R1 R2 R1 Rg, you can see that here, and this R2 Rg, R2 Rg, this will actually take care of this part. Okay, this part when we multiply R1 R2, 5 R1 R2, so this is how it will get cancelled. Okay, this is equal to 5. Now if we put the values, look, R1 and R2. Okay, so R1 is given as 220 and R2 has got value 5. Okay, I'll just erase this part. Let me just do this calculation. So R1 is given, now I don't record this also. R1 is 220 ohm, R2 is given as 5 ohm. Okay, now I have to find out Rg. If I put this and solve for Rg, so what we get from here is, see, Rg is equal to, we can just multiply here. R2 is actually, let me just write it once. R1 is 220, R2 is 5 plus 220 Rg plus 5 Rg divided by 5 into 220 into another 5, so it will be 25 plus R2 is 5 into Rg, another 5 is there, 25 Rg. Okay, now you can solve for Rg and you will look that it will be 4400 divided by 200 ohm, and this will give you 22 ohm eventually. Okay. All right, we'll actually see the options. So here there is an option here, this 22. So option A will be the correct answer for this question. And we'll stop it here for today. Next day we'll continue with other questions, other remaining questions on this chapter. So thank you for your patience. Bye for today.